Lab guy here. The NBTV cathode ray televisor is completed. In the last video we did a physical walkthrough looking at the various real estate within the unit and generally discussing the function. Tonight we will do a deep dive. This will probably be a very long video. Sorry about that, but we're going to go into every circuit in detail and go through them. As I mentioned in the last video, I will present this in a series of blocks which you are free to copy and modify and use for your own projects. I recommend this highly. And I'll show you what the finished televisor looks like on the outside. I couldn't let it just remain an ugly metal box, so I did a little cleanup work to it, some finishing work, and shot some glamour video for you, which you will see in a moment. And then after the deep dive theory of operation, I will present a slideshow of various still images taken from the screen of the cathode ray televisor. Taking still pictures will show you the quality of the actual images with none of the flicker issues. I've tried several different ways to record the moving video with my existing equipment, and it's not working, so we'll just skip that for now. I'll keep looking for a way to photograph these systems, but I would like to button this project up tonight and move on to the 10-4 Eleanor, the RGBY NBTV signal generator, and I've worked out exactly how I want to do that, and it falls halfway between my original plan and many of the suggestions that were offered by many of the viewers, which I appreciate. But at some point you have to shoot the engineer and ship the product. So I'm at that point, and I'll build that project next, and we'll certainly look at that then. So after looking at some glamour shots of the finished NBTV cathode ray televisor, I will get into the circuit theory. Enjoy! Let's begin our deep dive in the power supply circuit. Looking at the left side, you see the AC entry module. This provides us with a convenient EIC power cord input receptacle, a common mode noise filter, a power switch, and a fuse, all in one convenient unit. Moving to the right, we have the Hammond power transformer. It's a model 261C6, 261 Charlie 6. It has a 120 volt primary. It has a 6.3 volt 1 amp secondary for running a tube heater, in this case our cathode ray tube. It has a 250 volt center tapped high voltage winding. In our case, we are operating this winding single-ended. That is, instead of grounding the center tap, we're grounding one end of the winding to give us two different AC voltage outputs, a 125 volts nominal and a 250 volts nominal. The voltage of each winding is closer to 135 volts when lightly loaded. Moving to the right on the top section, we have a standard voltage doubler. You'll notice that the components are doubled up. This is due to the fact that I didn't have single components that met the voltage requirements. The diodes are 1 kilovolt peak inverse voltage diodes, and our peak inverse voltage in this case is about 1600 volts. In the original version, the diodes kept failing, so I doubled the diodes to give me 2 kilovolts PIV rating. The capacitors are 47 microfarads each at 400 volts. Our output voltage after doubling with very light load is 760 volts. This is because the 125 volt winding of the transformer is actually operating closer to 135 volts per winding. No problem. The capacitors are placed in series to double their working voltage, and a pair of 10 meg resistors is placed parallel with them to equalize the voltage drops to prevent one capacitor from ending up with all of the voltage across it and causing it to fail. The circuit works very well because the capacitance with the two 47s in series like that, we have 23 microfarads of filter capacitor at nearly 800 volts. This power supply puts out 760 volts with a half a volt of ripple. Moving down to the next DC power supply, we have a half-wave rectifier into another 47 microfarad 400 volt capacitor. After rectification, that capacitor has about 380 volts on it. We drop the voltage to 300 volts with a pair of 150 volt Zener diodes and limit the current through a 10K 2 watt resistor. The 300 volts goes to the deflection circuits. Each deflection circuit draws a constant 1 milliamp, so there's only a 2 milliamp load on that circuit. In addition to the Zener diodes, I have a 1 megohm bleeder resistor which is pulling an additional about 300 microamps. The job of that resistor is to discharge the 47 microfarad capacitor. Moving down to the third rectifier, we are running this one on the alleged 125 volt tap, which is more like 135 volts as I mentioned, and we're getting about 190 volts rectified on the 47 microfarad capacitor. Again, we use a Zener diode, in this case 150 volts, a 5K series current limiting resistor, and produce 150 volts with the Zener diode for running the video amplifier. This circuit also has a 1 meg bleeder resistor for the capacitor. Moving down to the bottom of the schematic, we see PS1, which is our low voltage power supply. It is an MTMA1511 by Astrodyne. This is a medical grade switching power supply. Being medical grade means that on the low voltage side, it is safe to make connections to a patient. For instance, in an EKG machine. This is not a critical point in this use. It provides our plus 5 volts and plus and minus 15 volts for all of the ICs that I use on the video board. Let's move on to the video deflection board. This board contains 5 major subsections. They are the video input process and sync process, the frame deflection circuit, the line deflection circuit, the video amplifier circuit, and the audio amplifier circuit. We are looking at the input video and sync processor. It starts on the left side with the video input, the termination impedance selector switch, the video input buffer amplifier, a DC restoration circuit, a sync separator circuit, and a frame sync detector circuit. The video comes in through an RCA jack labeled J1 video input. It can be terminated in either 75 ohms or 10K. This is controlled by switch 1, which selects our either high or low impedance input termination so that we can either use a proper video generator or an audio card or tape recorder output. This incoming video signal is AC coupled into the first amplifier, which is a unity gain amplifier, and its output is AC coupled to the DC restorer. The op-amp U1B is configured as a negative peak detector. When an input is AC coupled to this type of circuit, the most negative excursion of the signal will become referenced to the voltage present on the positive input of the op-amp. You'll note that pin 5, the positive input of this op-amp, is wired to ground or 0 volts. So in this case, the bottom of the sync tips of the video signal will be clamped to 0 volts DC. This holds the video steady for the next stage, which is the sync separator, an LM319 comparator chip. It takes and samples a signal on one input and compares it with the reference voltage on the other input. Depending on the polarity you use, positive versus negative, either input can be reference or either input can be the signal, will determine the output polarity. In this case, I've configured this device so that the signal is applied to the negative input and the reference voltage is applied to the positive input. The reference voltage here is just a fraction above 0 volts. You'll note that the divider consists of a 2K resistor in series with a 100 ohm resistor, so that the voltage on the 100 ohm resistor is only 100 or 200 millivolts above 0 volts, which puts it inside of the sync tips. So when the sync tip goes more negative than the voltage present on pin 4, the output of the comparator on pin 12 will be pulled high. As long as the video is above the reference voltage on pin 4, the output remains low. So for every sync pulse that comes in on pin 5, the output will pulse to a high logic level of 5 volts. This separated sync is sent to the frame sync detector and to the line scan circuit. The frame sync detector is configured as a missing pulse detector using a 555 timer. The sync for NBTV provides frame sync by leaving out one of the line sync pulses. When line sync pulses are coming one after another every line, they switch transistor Q1 on briefly during the sync pulse, which discharges C19, the 4.7 microfarad capacitor. You'll note that it is connected to RV5 and R23, and when the transistor is switched off, the capacitor begins to charge. As long as a sync pulse comes in before the charge reaches the threshold level on pin 6 of the 555, which is 1/3 of the 5-volt supply, then nothing happens. The 555 does not switch. During the time when the sync pulse is missing, it's now 2 lines long between sync pulses, and the capacitor has time to charge up to above the threshold voltage of pin 6 and triggers the 555, which then outputs a low-going pulse, which I call frame sync not. And this happens once per frame, and frame sync not is sent to the frame scan circuit. Frame sync not pulse comes in from the left side and resets our frame oscillator. The frame oscillator is set to a natural free-running frequency of 12.5 Hertz. If frame sync not is not present when video is not plugged in, then the oscillator will free run so that we continue to scan on the face of the CRT. The output pulse from the frame oscillator, a 555 timer IC, is an active low-going pulse called frame drive not, which we can look at on test point number 3. I invert this pulse with U5D, just a standard inverter chip, and turn it into a positive going pulse and feed it to Q3's gate, a 2N7000 field effect transistor. And once again, we have a capacitor that is charging up. When Q3 is turned off during the active line time, the capacitor charges up through a constant current source consisting of RV8, R29, R32, and Q2. This establishes a constant current for charging the capacitor. A capacitor charged with a constant current will charge at a linear rate. The capacitor charges from 0 volts when Q3 turns off and charges up to 5.6 volts maximum. The diode is there to clamp the charge on the capacitor at 5.6 volts to prevent overdriving the frame deflection amplifier, which we'll get to in a moment. The rate of the ramp is adjusted with RV8, which sets it so that the ramp charges from 0 to 5 volts inside the frame time of 1/12.5 of a second. 1/12.5. Yeah, that's a real number. So this charge from the capacitor is buffered by U6B, an op-amp configured as a voltage follower, which drives RV10, which is our size control pot. Looking at the frame deflection amplifier, you'll note that it is a differential amplifier. At the bottom in the center is another constant current source. This one is hardwired for approximately 1 milliamp of current. This 1 milliamp goes from the -15 volts through the current source up to the point that says 1.35 volts, where it splits in two. If the base of Q6 and the base of Q10 are at exactly the same voltage, they're in balance, that current will split equally, and 0.5 milliamp, 500 microamps, will go through Q6, 500 microamps will go through Q10. 0.5 milliamp flowing through the 150K resistor will produce a voltage drop of 75 volts, giving us 225 volts on the collector of Q6 and conversely the collector of Q10. When the input signal on Q6 goes positive and the voltage is held constant on the base of Q10, then the current will divide proportionally between the transistors. Q6 will draw more current, the voltage drop across the 150K resistor R36 will increase so that the voltage at X minus will go down. And because the current is constant and Q6 is taking more than his fair share now, the current going through Q10 will drop, and the voltage drop across his collector resistor, R44, will decrease, making the voltage at X plus go up by the exact same amount as X minus went down. So we have a doubling effect between X minus and X plus on the signal level. This point here can generate up to about a 200 volt peak to peak differential, which is applied to the deflection plates of the cathode ray tube. That is how the deflection is created. When we look at the cathode ray tube circuits, you'll see that X minus and X plus are AC coupled through two capacitors to the deflection plates of the CRT. And so that is how the frame deflection circuit works. Now we are looking at the line deflection circuit. It is mostly the same as the frame deflection circuit, except that it runs at a different frequency. There is one other notable difference. You'll note that line sync on the left, which is a positive going pulse, is changed to a negative going pulse by U5A, the inverter, and is now AC coupled to our 555 oscillator. The reason for this is that when there's no video input, line sync goes high, and that would cause pin 2, the output of the inverter, to go low and stay low, which will reset the 555 and prevent it from oscillating. We want it to oscillate when there's no video present. So I've tied the reset pin, pin 4 of the 555 timer, to 5 volts with a 10K pull-up resistor, and AC coupled the reset pulse. The reset pulse here is line sync. This is arriving at 400 Hertz minus the 1 sync pulse used for frame sync. That's the reason for this oscillator, in the sense that if that frame sync pulse doesn't arrive, this oscillator naturally runs at 400 cycles as well, and it will simply oscillate for the 1 missing pulse, producing a continuous train of pulses on its output at pin 3. The output pulses go low when they are active. So again, and we call those pulses line drive not. Once again, we invert the pulse to make it positive to drive our FET switch, the 2N7000 Q5, to reset our line ramp capacitor. You'll note that this capacitor is 10 nanofarads, much smaller than the 4.7 microfarad in the frame circuit. This capacitor also charges up through a constant current source consisting of R31, RV9, R33, and Q4. This current source is also adjustable and provides the necessary current to cause this capacitor to charge up in one line. It also has the clamp diode to prevent the charge from going higher than 5.6 volts and overdriving our line deflection amplifier. The capacitor charge is again buffered by a op-amp configured as a unity follower. That is, that whatever voltage goes in, that voltage comes out. It's simply buffered. This keeps the pot RV11 from loading our capacitor. Our capacitor would not charge up if that pot was connected directly to it. So the buffer amplifier feeds the pot with our drive signal. The operation of the line deflection amplifier is identical to the operation of the frame deflection amplifier. It is a differential amplifier, high voltage, driven from a constant current source on its bottom side. Here we are looking at the video amplifier circuit. Its job is to take 1 volt DC restored video, called DC video, and increase it to several dozen volts to drive G1, the the control grid of the cathode ray tube. DC restored video comes in on the left side and goes through a unity gain buffer op-amp that drives the contrast control. The returning contrast controlled video, which I call gain video, enters our op-amp, which is configured as a gain of 2 inverting buffer. The feedback of this inverting buffer comes from the emitter of our high voltage transistor, an MJE340. The gain video coming in is positive video. It comes into this op-amp circuit, which inverts it. The incoming video is 0 to 1 volt. After it is inverted and comes out of pin 1, it is now running 0 to minus 1 volt. This signal crosses our base emitter junction and goes to a 14.3K resistor, which goes down and ties to minus 15 volts. We are dropping 14.35 volts across this resistor, which gives us 1 milliamp flowing up through the transistor. That's at 0 volts on the base. Okay, think DC for a moment. That 1 milliamp goes up through our 100K resistor to the 150 volt rail, and 1 milliamp across our 100K drops 100 volts. So our collector of Q12, the MJE340, is sitting at 50 volts DC. When the video signal on pin 1 goes negative, this causes the current to decrease. As it drives negative, there's a smaller voltage drop across R51, and this causes less current to flow through the emitter and collector circuit, causing less voltage drop across the 100K, and the voltage at the collector now goes more positive. So our op-amp is operating as an inverting circuit, and Q12 is operating as a second inversion circuit, so that the net result is that the signal is not inverted, or it's inverted twice. It comes out positive, but amplified by about 15 times, approximately 14 or 15 times. So our 1 volt signal is coming out with an amplitude between 14 to probably 20 volts or so. It is adjustable. I have not measured what the exact voltage is. That voltage, now our amplified video signal, which is now a dozen to a couple of dozen volts, is AC coupled to G1, the control grid of the cathode ray tube. You'll note the intensity control DC voltage is fed back from the scope module through the 3-pin connector and is stored on a 47 microfarad 250 volt capacitor. This creates a DC reference, which is where our negative going sync pulses forward bias D9 during the sync time, forming a clamp circuit. When that sync tip goes the most negative, this will forward bias the diode in the negative direction and clamp the output plate of the 47 microfarad to that voltage. So our intensity control affects the negative voltage of our amplified video signal. This sets the DC level for that signal, and we can alter that with the brightness control. The contrast control alters the amplitude of the amplified video signal going to G1. So we can control both the DC offset and the gain of that video signal going to G1. That is how this video amplifier works. Here we're looking at the schematic of the James Millen 90901 oscilloscope module. This schematic represents the modified version that I created in this system. You'll note that the modification is in the intensity control circuit. Looking at RV1, the intensity control, you'll note that the line goes straight across to G1, or it used to, and that was the brightness control for the oscilloscope tube. That was before video was applied. The intensity control outputs a DC voltage that goes back to the video amplifier to control the offset of the amplified video signal. The amplified video signal comes back through pin 2 of the connector and is fed to grid number 1 to control the intensity of the electron beam. Pin 3 on that connector is simply to provide a signal return ground back to the video amplifier. Our 760 volts DC from the power supply enters a voltage divider chain that consists of R1, R2, R3, R4, and RV1, as well as RV2 and RV3, which are in parallel with R1 and R2. The voltage developed between R1 and R2 is applied to our second anode pin, A2. A2 is a shared pin, which also is part of grid 2 and deflection plate 1 prime. A2 and G2 form part of the focus electrode in conjunction with a grid which would be G3 if it were labeled, which is tied to the cathode. This electron gun is configured as what they called a self-focusing gun. You'll note the absence of a focus control in this circuit. So, the points A2, D2, D1, and D2 are the 4 deflection plates, ignoring that A2, G2, and D1 prime share that pin. So the pin labeled A2, think of it in this case as D1 prime, and D2 both provide a fixed DC voltage to their respective deflection plates of D1 prime and D2. Don't worry about the polarity of those plates. Those are arbitrary in order for the scan signals to make a right side up image on the tube. D1 and D2 prime are the driven plates that have the centering controls, the vertical centering on D1 and the horizontal centering on D2 prime, which are adjustable DC levels. They are buffered from the incoming deflection signals by the two 3.6 megohm resistors. So the 4 deflection signals from our differential amps enter at the top through Y minus, X minus, Y plus, and X plus, and are AC coupled through C1, C2, C3, and C4. They're added to the DC components that are present at the node between R1 and R2, a buffered node with another 3.6 meg resistor going to deflection plate 2, and the 2 DC reference voltages at the node of R6C3 driving deflection plate 1, and the DC control voltage at RV3 through the 3.6 meg resistor and summed with the signal through C4 going to D2 prime. This is how the AC components of the deflection and the DC components of the deflection are added together to drive the tube at the correct DC and AC voltages. Here's a quick look at the audio amplifier, which I have not implemented yet. It's a classic single chip LM386 audio amplifier chip that takes the audio input, runs it through a volume control, amplifies it, and drives the speaker. This particular chip is LM386N-4, and it must be an N-4 because this version of the chip has to run on 15 volts. The N-4 is the only one that will operate on a voltage higher than 12 volts. That's all that we can say about this amplifier because I haven't even implemented it. This completes the look at the audio amplifier and the description of the NBTV cathode ray televisor. you're still here. Well, congratulations. If you've made it this far through this video, you are one tough bastard. And I mean that in a good way. Honestly, I do. This video has taken several days to edit. I put in 3 or 4 hours every day editing this monster, and you wouldn't believe how many times I pause when I'm talking and saying It takes forever to edit that crap out of the soundtrack. So that's one aspect that adds up the time, and the other is the that little moving arrow on the schematic. You wouldn't believe how much work that is. It doesn't look like it, and it isn't, you know, in terms of work, but I mean, it takes time. It eats up time worse than Einstein. So anyways, we have good news. We have very good news at this point, besides that the cathode ray televisor is completed. We have 2,504 subscribers today on the last day of October 2020, October 31st, 2020. We have 2,504 subscribers. To all of you, I say thank you. Thank you, thank you, thank you. I can't tell you how much I appreciate this. I know it's just an arbitrary number out there, but by golly, it's a milestone anyways. And I'm still astounded that that many people find my subjects interesting, though I do try to make it that way. So there you have it. That milestone has been reached. I'm going to cut this out. So thank you for watching. Thank you for subscribing. If you know anyone who likes this subject matter, please point them at my channel. And when it comes to all that rest of that just, you know what to do. Unlike the other channels, I'm not going to say those words anymore, because I know that my viewers are not stupid. Okay? You guys are some of the sharpest viewers on YouTube, and I don't need to tell you how to push the buttons. So, thank you again. I'll try to make the next project even better. So until next time, Lab Guy out.